Hey everybody. Last week we introduced exponential functions and we talked about how to identify each piece of the exponential function when it was written as y equals a times b to the power of x. A was the starting amount. B told us whether it was exponential growth or exponential decay. Right? If b was bigger than 1, it was exponential growth. If b was a number that fell between 0 and 1, so some sort of decimal or fraction, it was exponential decay. And x is what we plug in based on the amount of time or whatever we were dealing with, whatever our independent value was. Now, this week, we want to start talking about some real-world problems and learn how to set up these equations on our own. And then in the weeks to come, we'll talk about how to evaluate the equations that we set up today to figure out the value of something after a certain amount of time. And so, when we do this, we actually have two different formulas, one for exponential growth and the other for exponential decay. And so when we talk about exponential growth, we have y equals a times 1 plus r to the power of t. And when it's written this way, a is still our initial value, so whatever we're starting with, but r is our rate of growth, and it's usually going to be given to you as a percentage, but you will have to turn that into a decimal. And then t is the amount of time that we're talking about. Exponential decay is going to be a very similar formula, except this time we're going to see that it's y equals a times 1 minus r to the power of t. And so a is still the initial value, r is now called the rate of decay, and t is the amount of time. And so when we do these formulas, we'll see that they still give us exponential growth or decay formulas. We'll simplify them down to that, but the setup will look very different. So here's example 1. The original value of a painting is $9,000. All right, if I know that's the original value, I'm going to underline that because that tells me something important. And the value increases by 7% each year. Write an exponential growth function to model the situation. And so because this is exponential growth, and we know that not just because it tells us it's exponential growth, but because it says the value of the painting is increasing, it increases. So because of that information, we have to use the formula y equals a times 1 plus r to the power of t. Well, a is my starting value, and I know that the painting started at $9,000. And r is the percentage that they give me, which was 7%, except I cannot use it as a percentage. I'm going to have to change it to a decimal. Now, there's two ways to do that. The first way that you can do it is probably how you learned it in middle school. Every whole number or every number has a decimal, whether it's written or not. And so a number like 7, it's just there at the end. And we move a decimal 2 places to the left to get rid of a percentage sign. And if there's any open gaps like there are here, we fill it in with a 0. And so then my r value is actually 0.07. Now, the other way that you could do this is you take the percentage that's given to you, so that number 7 again, and in your calculator, you type in 7, and then you divide it by 100. And that's going to give you the same number, 0.07. So whichever way you prefer to do it, you're welcome to, but you have to make sure you change the percentage into a decimal. And so now, let's plug in the information that's given to us. Our A value is 9,000. Our R value is 0.07. And so that leaves us with an equation that looks like this. Y equals 9,000 times 1 plus R, which was 0.07, to the power of T. The next thing that I need to do, though, is I want to simplify what I have in parentheses here so that it looks more like the problems we saw last week. And so that gives me Y equals 9,000. Well, 1 plus 0.07 is just 1.07 to the power of T. And so now we can see that our B value, like we saw last week, is a number that's bigger than 1. And it's not a lot bigger, but it is bigger. So B is bigger than 1, which was exponential growth. And this here is all we're doing this week. We're setting up these equations, and we are going to use these equations in the future to figure out after 5 years or 10 years how much that painting is actually worth. So that was example 1. Let's try example 2. The number of employees at a certain company is 1,440 and is growing at a rate of 1.5% per year. Write an exponential growth function to model the situation. So now I'm going to use my formula again. Y equals A times 1 plus R to the power of T. Well, what is my A? 1,440. And what is my R? Well, R, it looks like is 1.5%, but again, I cannot leave it as a percentage. So I take 1.5, I move the decimal over 2 places, and then I fill in that 0. And so my R is 0.015. And that leaves me with the formula Y equals 1,440 times 1 plus 0.015 to the power of T. So what am I left with when I simplify it? Well, 1 plus 0.015 is just 1.015. So Y equals 1,440 times 1.015 to the power of T. And now this is the equation, the function, that's going to model the exponential growth of the employees at this company. Let's go to example 3. A new car is worth $25,000 and its value depreciates 15% each year. Write an exponential decay function to model this situation. Well, this word depreciates, you may not be familiar with it, but what it means is that the value of the car is shrinking. And so if you ever listen to a financial planner, if they're a good financial planner, they'll tell you that you should never invest in a car to make a lot of money. Because most cars, the minute you drive them off the lot, they lose value. So even if you started by paying $25,000, once you drive it off the lot, it's no longer worth $25,000. And once you've had it for a full year, it's definitely not worth $25,000. And that's why cars that are 10 years old tend to be somewhere between $1,000 if it's in bad shape, or $5,000, or somewhere on a much smaller scale than a $25,000 car, even though it's only 10 years old. And so I also know that it's depreciating at 15% each year. But because it's depreciating, I know it's shrinking, and so this is not exponential growth, it's an exponential decay function. And so we're going to use the formula y equals a times 1 minus r to the power of t. The value of the car starts off at 25,000. So let's see if you can figure out what this equation is. 25,000 times 1 minus, and I can't use 15%, so I'll write 15. I'll put a decimal, move it 2 places to the left, and so my R value is 0.15, so I didn't need to fill in a 0 this time, to the power of t. Well, when I simplify this, 1 minus 0.15 is going to leave me with 0.85 to the power of t. And so this time, my b value of 0.85 is smaller than 1 and yet still bigger than 0. So it's a decimal that falls between 0 and 1. So in fact, it was exponential decay. So let's look at one more example, and then you can work on the assignments for this week. There are 2 of them. One of them is minor grade. The other is going to be a major grade. It's going to be a quiz. So example 4 says the deer population of a game preserve is shrinking. So these deer are dying off by 2.5% per year. So let's change that right now. 2.5 already has a decimal. Move it 2 places to the left. And again, you can use your calculator if you want. And so what I end up with is 0.025 is my R value. The original population was 1,850. And so I'm left with my A value being that. Right? And so if you are somebody who studies the population of animals, zoologists, or if you are like a game warden, these kinds of equations are important. So we get y equals 1,850 times, and this time it's exponential decay, so we want 1 minus our R value, which was 0.025 to the power of t. What does that simplify down to? Y equals 1,850 times, and you might use a calculator for this, but 1 minus 0.025 is 0.975 to the power of t. And so, again, we're done. All right, so good luck on your assignments this week. If you have any questions, make sure to email me. We can set up a Teams conference, and we'll do tutorials again this week at 1 o'clock on Wednesday. I hope to see you then.